All right, so the last video, I don't know if it's the last one. We'll see. We'll see how far we get, okay? I'm going to try to wrap up the derivation for understanding the spectrum of two particle systems in a finite volume. Let's just recap. Hopefully I convinced you that you can access the spectrum in a different set of ways, right? Using Euclidean correlators as well as Minkowski correlators, both time, energy dependent ones. This is of course what allows us to extract the spectrum from Euclidean correlation functions, right? And so this is what allows us to get away essentially with murder in our lattice calculations, right? We can access quantities that are time independent easily, right? Time dependent quantities, life gets harder. Not impossible, but you can't do always. So the work that I'm following is that by Kim, Socrates, and Sharp, right? And the idea was we're going to look at the energy dependent correlation functions of two particles in some kinematic region where you can have only two particles go on shell, but no three particle, for example. We looked at, we were able to write down the correlation function as the sum over all bubble diagrams with all the details hidden in the inside of these kernels, which are volume independent up to exponentially small corrections, which we're neglecting. We looked very closely at this diagram, and I, basically walked you through the derivation of how to write this, this diagram, which is what we want in terms of the infinite volume diagram, up to a finite volume correction where the external legs have been placed on shell, right? And you have some known kinematic function, okay? This known kinematic function is a matrix over angular momentum, right? It's not diagonal because in a finite volume, angular momentum is not a conserved quantum number, but, such is life, right? But this encodes all the mixing between different partial waves that there could be. And so, okay, so I glossed over not many details. In fact, I've been trying to be as rigorous as possible at the cost of not showing you as much as possible, but hopefully, this gives you a, as much understanding of at least one sliver of spectroscopy, which turns out to be remarkably important and powerful these days. Okay, and so in short, we can write down the difference between the finite volume function and the infinite volume loop. So the finite volume loop and the infinite volume loop in terms of something where you place the external legs on shell and you multiply times some finite volume function. And so in short is this, okay? So diagrammatically what we have in our correlators is this object. So then I just move the infinite volume piece to the right, from the identity above, and I get this identity. I have that this is equal to this plus a known thing. So this thing, which in general I don't know, is equal to the infinite volume function, which I don't know, but I want, plus something that I do know, which is this finite volume function, okay? This f. So let's skip ahead. Okay, so now what we're gonna do is just grab this identity and place it everywhere inside of our 2-point correlator. Okay, so we'll start with the first one. So our 2-point correlator is just equal to all the sums of our bubbles, right? And so let's look at this first one. I just apply the identity that I just derived, right? And then I do that for here, 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 everywhere, right? I just applied this. And it's useful to think about, now I'm going to, repackage all these diagrams in a way that is elegant. So I'm going to essentially grab all the terms first that have no F's in it, okay? So I'm going to grab all the 0th order terms in F, right? In other words, every single diagram, where I just replace this with the infinite volume. All right. And so that's equal to this object, right? It's just a sum over the infinite volume bubbles. But this is nothing more than the infinite volume Minkowski correlator. This object is closely related to the scattering amplitude that we've been thinking about, that we thought about in the past, right? This has to be the case from LSZ, right? And so this has the same analytic structure, so it has a branch cut on the real axis of the -some variable s. This is really a Lorentz scalar, so this is a function of p squared. Let's just write it out. Okay, and so this will have a branch cut. It could have poles, etc., right, associated with bound states and resonances. But this is not everything, right? This is only, in here are only the terms that have no f's. Well, what comes next? All the terms that have a single f, just one f. Okay, so I can put an f either here, right, or here, right? And I just pick one bubble where I put an f, and then everything else I replace with infinite volumes, right? So that's what I'm doing. Here's one f, here's one f. Now on the right hand side I have now an infinite volume loop, and then on the left, now in this case I have an infinite volume loop multiplied times an f. Okay, so what is this doing? This is essentially dressing this kernels associated with the production and annihilation of two particle diagrams, right? Those had I should have been perhaps more explicit, right? But these kinds of diagrams, this is not a contact term alone, right? Like imagine this little is a kernel, just like what we had for the beta subpeter kernel, where you have some sort of distance object, right? And then you have productions of three particles, right? A bunch of diagrams will appear here. That are embedded in this object, right? This is a non-perturbative quantity, but what is missing is all the S-channel diagrams, because those I put in explicitly, right? I highlighted those explicitly in here in these diagrams. So what's happening now is that now you're starting to see that, for example, this leg is now being dressed by this S-channel diagram, while this one is getting dressed by this S-channel diagram, and indeed what you have is the sum over all S-channel diagrams emerging from this expansion. And so the left hand side now gets dressed, right? And on the right hand side becomes stressed. And so in doing this, this is all the diagrams that are coupling the vacuum to two particle states via the insertion of some external operator. This is indeed an amplitude, right? This is a physical amplitude. So if it depends, what current I put in, right? But if it's a renormalizable current, then it could be a well-defined amplitude. So for example, I could have put in imagine that I'm creating states with the quantum numbers of, say, the electromagnetic current, right? And so this could be my production amplitude, right? And so the state that I would create would be, let's say, it would have to be a pi with a, and a p wave to have the right quantum numbers. And so this amplitude could, for example, represent the transition between a photon to two particles, two pion system and a p wave, a physical reaction. Okay, so that's what that is. Okay, and so, but in general, this doesn't have to be physical. It doesn't have to be a renormalizable current that is creating the states. It could be non-local operator that doesn't have a well-defined renormalization. That's perfectly fine too. But anyways, there's just some amplitude. All right, so now I've reordered things, right? I put in the linear terms in F's. Next, we have to look at the terms that are coming with two F's. And so here they are. Okay, so that starts. I have to start considering these, the second terms in the diagram and in the expansion above at least. And so I would, I could have two cuts, right? So that's what this diagram is. Or when I have three bubbles, right, now I have all possible cuts, right? So I'll have basically, I'll have three terms. I've only shown here two, because you can, the infinite volume one loop has to appear somewhere inside of those three diagrams. And so what you end up having, right, is that now you're starting to, you see here, I'm dressing the left-hand side, right? And I'm dressing the right-hand side, right? And then I have these amplitudes, these A's are being separated by F's, right? And what's in between the F's now is the on-shell partial wave projected kernel, beta Sapir kernel. But this is not everything, right? I'm forgetting a class of diagrams. And in fact, the other class of diagrams that I'm neglecting are those where this kernel is now being dressed by S-channel infinite volume diagrams, right? So you can see that this term, right, that already appears, a contribution to this term appears in this diagram, where I replace the intermediate finite volume bubble with the infinite volume one, okay? To see the contributions for this, I would have to go to 4 S-channel bubbles, okay? So this is a great point for you to stop, right? All I'm doing is just grabbing this simple identity, right? Putting it into all the diagrams, right? And just repackaging things in a convenient way. Okay, that's all I'm doing at this point. So I would ask you perhaps to stop the video, check this if it's not totally clear, right? And it's just, it's just fun to check how these, all I'm doing is just reshuffling of diagrams. And so, it's a fun exercise. So I'd encourage you to do it yourself. Okay. And so, the idea, right, is that I have now the infinite volume 1 plus 1 where I have finite volume cuts, essentially separating infinite volume quantities, right? And so then I have, you have the production of 2 particles, finite volume cut, annihilation, right? Next you have production, finite volume cut, rescattering, right? Some infinite volume scattering process, finite volume cut, and then annihilation, right? And then this starts to happen any number of times. And so, yep. So what ends up happening is that, I think I made a little boo-boo. Let's fix this. So I'm over counting. This term right here is in here. So let's fix that. Look at this. You gotta love a good iPad, right? Oh no. This propagates. Okay. So I cleaned up my boo-boo. And so, okay, so what I have now is infinite volume production, F cut, right? And then here I've kind of skipped a little bit, right? I'm starting to see a pattern emerge, which I encourage you, of course, to check, which is what appears separating the 2 F's, right? Is a series where I have the scattering amplitude and then scattering amplitude, F cut, scattering amplitude, and I have that essentially as a geometric series. It looks like exactly what we did for M, right? Where there I had row cuts separated by the K matrix, right? Here I have, so it was row was a kinematic singularity associated with intermediate particles going on shell, separated by a short distance object, which is a K matrix, right? Here what I have essentially is F cuts separated by, which are finite volume singularities, separated by infinite volume scattering processes, or scattering objects, not processes. Okay, this is essentially what's happening. And so convince yourself that indeed this right here I can write as a geometric series, right? And then what I'm trying to find is the solution, the locations for the poles of this object, right? I'm interested in the spectrum of the correlation functions and the spectrum of the theory, which it either amounts to finding the poles of the energy dependent correlation function or the time dependent, or I can get it from the behavior of the time dependent correlation functions. Okay, because the infinite volume correlation only has cuts, this can't be the source of the poles. And so here actually it takes a little bit to make this argument clear. Namely, if I don't have bound states, then this object doesn't have poles. Okay? The transition amplitudes, these objects, also don't have poles. They're infinite volume amplitudes, and they have the same analytic structure as the scattering amplitude. And so they won't have poles either. And so the only place where there can be poles is this. Okay? Meaning, from where in the inverse of this matrix, this is really a matrix identity, right? These are matrices over the available degrees of freedom, and I'll make that very, very explicit in a second. And so this is really, here I'm being a little sloppy. Let's be less sloppy, because that's what you guys are having here for, right? Is to not be so sloppy. So this is really the inverse of a matrix, right? And so this matrix can have poles, right, when it's not invertible. And so that amounts to when the determinant of it is equal to 0, okay? And so the only subtlety here, right? So the claim is that the poles come from this object alone, and they'll be on the real axis. And so those, because I'm considering the Minkowski correlator. The only subtlety is when you do have bound state poles. And there you can show that this will have poles, this would have poles, this would have poles. And you can get the residues of these poles are closely related in such a way that essentially the infinite volume bound state poles, this doesn't go to infinity, but it actually goes to 0. So you get a pole with a 0 residue. All the poles exactly cancel. And in fact, the bound state poles in a finite volume are shifted by the quantization condition. Okay, this is a very subtle point. So if you're very, very comfortable with this scenario where there's no poles, we can talk about this later on. I'd be happy to show you a sketch of this argument. Okay, so then all we have to then do is just grab the determinant of this object. Again, here I'm being sloppy, but whatever. You know that this stands for the inverse of the matrix, right? And so this matrix is not invertible when its determinant is equal to 0. And so voila, this is my quantization condition. This tells me the equation that the spectrum must satisfy in a finite volume, at least in this kinematic region, right? Between 2-particle threshold and the 3-particle threshold. In fact, it holds even a little bit below the 2-particle threshold. All right, so we have this determinant, right? And I told you that this is a determinant because this matrices are matrices in angular momentum, right? And so let me just, make that absolutely clear. So M, of course, is diagonal in angular momentum, and so it's just a diagonal matrix, okay? You will have the S wave component, right? And then the P wave, right, will come in with 3 components because you have 3 azimuthal degrees of freedom. And so they're all going to be equal to each other, right? And so you'll have, one component here and then 3 that are identical. Then for the D wave, you'll have 5. They'll be identical, etc., right? So it's a diagonal matrix. The F matrix, though, is not diagonal, right? As we've already emphasized, because you're in a finite volume, right? These objects will mix different partial waves, and so you just have to write them out and evaluate them. Okay, they satisfy various different. They satisfy symmetry properties depending on the different masses of the particles. Right now we're considering the particles to be identical, so that introduces a lot of symmetry, and that symmetry manifests in many of these terms being 0. So for example, for identical particles, so let me just first explain what this matrix looks like. So here I'm writing out the LM component of the final state and then the LM component of the initial state, right? And so this is S wave to S wave. This one is S wave to, or P wave to S wave, where the P wave component for 1 is not going to be the same as for 0, okay, depending on the boost. And so that's just the case, right? And so essentially you're breaking your rotational symmetry in general. So, a lot of things are out the window. And so, okay, so many of these things will be non-zero, but most of them actually will be 0. And so you'll be able to block diagonalize this matrices in such a way that you'll have products of determining conditions for each irreducible representation of the symmetry group of your system, which depends on the boost. Okay, there's a lot of jargon, but you kind of have to use learn to get familiar with these ideas, right? And so, yep, that's all I wanted to say. Okay, so for identical particles, it turns out that you have an exchange symmetry between the particles, and so that turns out that all the even and odd partial waves just don't talk to each other. And so that means that these guys will be exactly equal to 0. You'll always have components in the along diagonal that will be non-zero. The diagonals are always going to be non-zero. So it's really the off diagonals that would be that will be 0, and depending on the rep they're considering, the boost of the system, etc. So it starts to get hairy. So let's consider the simplest case, and then just to make life easy and just like end up on a warm and fuzzy note. So if we assume that all the partial waves are 0 except for the lowest one, and this is true, this is a not true in general, obviously, but it is a good approximation many times, because you have barrier factors associated with angular momentum that makes the scattering amplitudes behave like this at threshold. And so at threshold, they all have barrier factors, and so they're kinematically suppressed. So Q goes to 0 at threshold, and the L component will vanish like 2 to the L at threshold. And so at L equals 0, then this will vanish like, won't vanish necessarily at threshold, obviously, but then the other partial waves will. Okay, so if you're low energies, then if the quantum numbers of the particles allow it, then you will be dominated by S wave. And in general, you will always be dominated by the lowest lying partial waves, right? There's dynamical possible enhancements, right? If perhaps you have like nearby resonances, or even possibly bounce states associated with like higher partial waves, and this life starts to get more complicated. But this is to say that for a lot of systems, S wave dominance nearby threshold is very is true and useful to consider. So this is the case for pions in the in the I equals 2 channel and the I equals 0 channel. This is true for nucleon scattering. Same thing with kaons, k pi, right? Many partial waves, or many of these channels have dominance, and depending on the quantum numbers, are dominated by S wave. Sometimes you have S wave and P wave mixing. Okay, so then in that case, then this determining condition just becomes an algebraic expression where essentially you can just work it out, and you'll see that you'll have just one determining condition associated with the S wave channel. Here Fs just means the 0, 0, 0, 0 component of the F matrix. And so here you go from a determining condition to an algebraic expression, and what you can do is just manipulate this algebraically. I'm going to take the inverse of the scattering amplitude, write this in terms of rho cotangent delta minus I rho. And then on the right hand side, I'm going to pull F. So I have to bring it to the other side. So I get a minus sign, right? I've taken the inverse of the two. So I've done a couple algebraic steps, okay? And what I'll show you on the next slide is that you can write this object in terms of the principal value prescription evaluation for this function plus I rho. And so you have the rows will cancel. And so what you have is a very, very simple expression, which is minus F principal value evaluated is equal to rho cotangent delta. Why is this nice? Well, a lot of what's been done historically is if you grab finite volume energy levels, right? This gives you a determination on the lattice of a finite volume energy level. You can just put it in here, right? Tell me which volume it is, right? And this on the right hand side gives you, so by just evaluating the left hand side, that gives you a constraint on the phase shift at that same energy level. So that's pretty neat, okay? So that means that if I evaluate an energy level right here, right, I put it into here with all, I did all the hard work, did my, generational gauge configurations, did my contractions, my analysis of the spectrum, got, did my GVP, yada, 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 right? And I got this energy level. I put it right here, right? And then Lucier tells me, oh, that translates into a phase shift value over here, right? Which is going to go to some phase shift, let's say over there. Something like that one. Okay. So I have a direct mapping, right? Between this point over here and then this point over here. Direct, right? I didn't have to do any extrapolations, nothing. That's the beauty of this. And it's non-perturbative, right? We did this non-perturbatively. We never talked about like some EFT with some, low energy expansion, convergence, blah, 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 right? There's like some subtleties that I skipped over, right? But the claim is that this is exact, right? Up to exponentially suppressed corrections. And so if we're boxes where ML is sufficiently large, right? This should work perfectly, right? And it works pretty good. I mean, it works really well. And so this is the idea of the Lucier formalism. Okay, so here's a bunch of hairy stuff, right? Like this simple, manipulation of this function, right? Relied on some key subtleties, right? M is, okay. I really have no idea what happened to my camera. So let's see if this works. Hopefully we don't have any more issues. Okay. So the punchline, right, is that I grabbed this function, which is complex, and this function is actually complex. And I kind of overlooked at this a little bit, right? So I'm going to show you a little bit in detail. And so the point is that the imaginary part of this function exactly cancels the imaginary part of this function. And so you end up having a single condition for a single real energy level. That's great. So it's a fully constrained condition that we can evaluate phase shifts for. Okay, this is not always true, and in fact, it's generally not true. You will typically have a under-constrained relationship because you have this determining condition. Okay, and we know how to deal with that in these days, but it is a challenge, and there's in fact no connection. There's no one-to-one mapping. It's a one-to-many. That's just the way it is because you've lost the reduction of rotational symmetry. Anyways, so here what I did is I worked out in gruesome detail how to explicitly write this function in terms of purely real and purely imaginary part. Let me walk you through the steps a little bit, but I'll leave it up to you to work out. So from here to here, I just multiply the top and bottom by this quantity. Okay, I did nothing. So basically just multiply times 1 in a clever way. And going from here to here, I did two things. Okay, one, well, okay, several things. One, I rewrote the denominator in terms of momenta. That's easy. It's just kinematics, okay? Two, I said, I'm only interested in the limit where I'm near the pole, and that limit basically, oh, there's a typo. In that limit, E star in the numerator I can safely replace with 2 omega, so I did that, okay? And so I had like a factor of 4, and then the omega star, and so then I have omega star over omega. And then I pulled out this E over here, and then there was a factor of 2 from the denominator, a factor of 2 from here, a factor of 4 from here, and a factor of 4 from the numerator, okay? That translates as 4 in the denominator, okay? The other thing that I did is that I replaced a 1 here with this exponential. And the reason why is so that when I evaluate this numerically, I have to take the, I'm gonna just sum over momenta, over just different values of the momenta, okay? And so I want to not have to sum to infinity. So I'm literally gonna have to do the sum minus the integral to be able to evaluate this function. And so I want to have a cutoff here. And so I've introduced a cutoff where this is this parameter alpha, which we're gonna evaluate with a non-zero alpha, check the convergence, and then take that alpha to be 0 eventually, and test that the result is insensitive to alpha. Okay, so then that's what I did. In going from here to here, I separated the finite volume bit and the infinite volume bit. The infinite volume bit, I then wrote the pole in terms of the I grabbed this epsilon right here, right, and I wrote this pole in terms of its principal value piece plus the delta function, okay? For the finite volume, the epsilon doesn't matter, but for the finite volume, the epsilon doesn't matter. That's what I said, right? Okay, good, checking. And then for the infinite volume, I'll have the principal value piece and this row, okay? And then the principal value piece you can evaluate analytically, or you can, after plugging away at Mathematica after a little bit, you can show that it's equal to this, an exponential, and then the imaginary error function. All right. And then that's it. Okay, so the beauty of this is that now we've evaluated the integral analytically, and so we're going to subtract this analytically, and this is how we do it in our code. We can actually evaluate this analytically and just subtract it, and then the slowest bit is this sum. There's a subtlety here. I introduce an alpha that has dimensions, and so it's most natural to replace this in terms of a dimensionless alpha tilde. All right. So here was the bit, right, that I emphasized in the previous one. Oh, shoot. I forgot the I row. All right. It's plus I row on the sign above. Yep. And so this is what I emphasized in the previous slide, right? That you have the imaginary part. So the principal value piece is going to be purely real. The imaginary part is exactly equal to the phase space cut. And this, it shouldn't be too surprising, since the F is equal to the finite volume piece minus the infinite volume, right? And it's from this infinite volume, the imaginary part of this infinite volume, that we have the phase space cut, right? So that, which is the same source of the imaginary part of the scattering amplitude. And so the fact that this is canceling is nice, but it's not all too surprising. It had to have canceled if we did things correctly. Okay, so that's a great place to stop. And so what I wanted to just to reiterate, go over the problems that I glossed. I kind of went quickly at the beginning of the first lecture, which is, you should get comfortable evaluating the row cut analytically, right? I showed you how to do this in some detail, so go through it by yourself. So this is, giving me a check mark because I partly covered that. You need to, on your own, write code for the scattering amplitude for the Breit-Wigner and the effective range. Let's just consider a simple scattering length. You can forget about the effective range parameter, although that will be useful in general. So why not? And it's easy to code up, so you just might as well do it, right? And then next, evaluate the poles and residues analytically and numerically for the scattering amplitude. Consider a bound state, right? Just look at a positive scattering length and just, try to, just look at the plot of the scattering amplitude below threshold for a positive scattering length and see what you find. You know what this should be, right? From analytically, we've worked through this, and so you should be confident about that, and then just check it yourself numerically. This is a little more ambitious, which is show that the amplitude has a cut on the complex plane. This is harder, right? And that one subtlety here that appears is that the Q star is equal to S over 4 minus M squared, right? And so this is a cut at threshold. What do I want to say? What I want to say is that the square roots on C++ as well as in Python, they're aligned towards the left. The branch cuts are aligned to the left, okay? But what we need to do is align the branch cut on the right to be able to see this continuity, okay? And so what you have to do is effectively rotate this to the right. There's a cheap way to do this that will not work in general, and there's a right way to do this, which is just grab a point, right, in the complex plane. Let me stop doing that. Grab a point in the complex plane, right? And so if the phase is between 0 and pi, don't do anything to it. Just find the magnitude in the phase, right? If the phase is over here, it's gonna, the phase that is gonna, if the point is in the bottom two quadrants, it's gonna give you a phase that is relative to this point, and so you're gonna have to rotate it. Okay, so all right, so that's something that you should check, that you can do on your own. Then the next thing is evaluate F analytically. We did this to some extent. It just means just work through the expression yourself. Code up F for L equals 0. All right. This L max just means that the highest partial wave that it contributes is an S wave. We already did this. And then the next thing you can start doing, right, is now start looking for the zeros of the quantization condition, right? Given some parameterizations, which you've already coded up, right? You already coded up too, right? What is the spectrum that you would get for a given finite volume from Lucier, right? So that's what I mean by pole finding for code. So it's just finding the poles of the correlation matrix or the correlation functions, which amounts to just finding the zeros of the determining condition, which is just finding this, the location of where this condition that we wrote down in the previous slide, namely this one, is satisfied. What values of P satisfy this condition? Not every P will satisfy this condition, but so you need to find which values are satisfy this. This exercise, I'm realizing it's not going to happen in this time frame, which is we were going to give you fake data, and you're going to be able to analyze it, some finite volume fake data, and you're going to analyze it and tell us what the underlying parameters is. I think this is unrealistic for this week. We can talk about doing this at some other stage when everybody's less busy with things to do. Okay. All right. So let me finish by recapping the big picture ideas, and perhaps I can lecture a little bit more, but I think this is a nice place to end. I was hoping to talk about transition amplitudes, but this might be perhaps a little too much for these 4 lectures. And so the big picture is that most states in QCD are unstable. All right, they decay to multi-particle states. All right, and so because of this, they need to be treated. In order to be treated rigorously, we need to understand how to think about them as resonant states of multiparticle systems, essentially. And the only way that we know how to define these rigorously is as poles in scattering amplitudes of their byproducts. And so if we want to study the QCD spectrum, and most of the states are resonant, we need to think about scattering amplitudes. And this puts a big showstopper, this puts a big limitation. It's not a showstopper, a big hurdle in the lattice, where scattering is not directly possible for two reasons. One, because we're in Euclidean spacetime, but also because we're in a finite volume. And in a finite volume, you don't have this notion of syntactic states. And so we're limited by that, okay? But what we can do is circumvent this to some extent by finding relationships between the finite volume observables that we can access on the lattice and the infinite volume ones. We've talked about to great detail how you can extract, how if you extract the spectrum, you can in principle get the infinite volume scattering amplitudes, right? And we derive this quantization condition that gives this relation. This is, of course, only useful if we can extract the spectrum reliably, which we can do now very well, given the amount of resources that we have, given around the development in technology, and some beautiful ideas like the generalized eigenvalue problem, which we touched on in these lectures. Okay, so this is something that is very fruitful, and a lot can be done. And what I'll mention last is the forefront. I don't know how to spell forefront. Forefront, like that? All right, so what I'll mention is the forefront, which is now scattering of not just two particles that are in a single channel, but also where you have multiple channels open. So you can write matrices of two particle systems. So this is something that we can do now very, very well. When you have, like, say, pions coupling to kaons, let's say. So these become matrices now over the open channel. So the black and red represent different types of particles. So like pi pi and kk pi, for example. So this can be done now very well. Something that can also be done is when you're coupling single particle states to a current and creating two particle states. And so this allows us to get at elastic form factors of resonances. This is more challenging, and this goes by the name of Lalouche-Lucier, at least the extraction of these amplitudes. And so you can get access to these from matrix elements of external currents. And so this is something that can be done. Of course, you can also couple single particles, or zero, so states with no particles to two particles, things like that. So this can be done. The real cutting edge now is starting to consider three particles. So 3 to 3. This has been now done for pi pi, the pi pi pi. Actually only for 3 pi pluses. Also for kaons, it's been done. Eventually we'll be able to do, coupling not just 3 particles to 3 particles, but also 3 particles and 2 particles. The formalism for this has been partly laid out. There's still some outstanding questions here. And what's recently been suggested is that you can even start studying currents coupling to 3 particles. Then there's ideas that are even other ideas that are possible is where you're coupling 2 particle initial state to to particle in the final state via current insertion. So this is interesting. So I should emphasize the reason why you care about these 3 particle type systems, right, is that ultimately, many resonances coupled to 3 particles. I mean, if you want to study even nuclear physics, right, if you can only think about 2 particle systems, that only allows you to think about things like the deuteron or dineutron. If you want to start thinking about helium-3 and so forth, then you have to start understanding 3 particles. This final frontier is cases where you can study 2 particle states coupling to 2 particle states via current insertion. And so this is allowing you to then start evaluating elastic form factors of 2 particle states, with the idea that perhaps you can, if there's resonances, you can start getting elastic form factors of the resonance. That's a function of the virtuality, where the Q squared is the virtuality of the current. And so by, for example, if you were to extract the charge form factor, and you look at the form factor, that's a function of virtuality from the slope of the form factor at Q squared equals 0. You can, from the slope, you can deduce the radius of the charge radius of the would-be resonance, for example. And so you can start now not just assessing whether there is a resonance, whether there's an excited state there, or you can start painting a picture of this state by saying, it has some sort of structure with some radius that is, roughly what you would, deduce from at least the charge is distributed in this, sphere with this mean radius around it. So this is quite exciting. I mean, this is this is really opening up many things that we can start doing to probe these states. And, many things are on the real axis of the considerations that we can start doing. This is made possible by 2 things, which is like the development of technology, right? But also the development of these theoretical frameworks. We need to have these robust ideas set in place for us to be able to start making sense of the correlation functions that we get out, right? So you need to have great hardware, smart algorithms, but you also have to have sophisticated mathematical frameworks to be able to make sense of the numbers that come out. And so hopefully, if you've got anything out of this talks, it's been that, right? Is that you need some understanding of how to extract non-trivial phenomena from lattice. It's certainly possible. There's no in the aspect of few body physics. There's no obvious limitations. There's many challenges, but there's no obvious showstoppers. I think it's a quite exciting field. There's many outstanding problems that I think we'll be able to tackle in the next few years. So I look forward to being able to talk to you more next week, at least face-to-face virtually. Okay. So with that, hope you have a good rest of your day, and I'll talk to you soon.